Hi, I'm Zihang from the University of Wisconsin-Madison, and this is a joint work with Lopa, Yichao, Vikas, and Sathya. Now, I will present our paper on algorithms for differentiable optimization of generalized non-decomposable functions using linear programming formulations. Here, the emphasis on differentiable is simply because if we think of the LP as a module in deep learning pipelines, we need to be able to compute the forward path and the backward path. Non-decomposable functions refers to those objective functions which must be computed from the full dataset and cannot be calculated easily from a small mini batch of data samples. So let's dive in. We see a lot of objectives commonly used in vision and machine learning that are non-decomposable. These include F-score, AUC, precision and recall, and many more. They serve an important role in many applications, including the information retrieval system, class imbalanced learning, measuring the performance of NLP models, as well as biomedical and scientific settings. Even though many applications need them, it is known that these non-decomposable functions are often hard to optimize in deep learning applications. Also, it does not decompose into a form which we can compute using small batches. This makes it hard to scale. The fact that they often require counting makes it hard to differentiate. To understand non-decomposable nature of the functions we study, let us consider the AUC for example. Calculating the AUC roughly proceeds as follows. First, we count the false positives and the true positives according to different thresholds. Secondly, we plot this curve which shows the relationship between the true positives and false positives. Finally, we perform integration to calculate the area. You can see that this procedure does not easily decompose into terms which depend on individual samples. It requires counting, which is not differentiable, under the standard definition of gradient, which follow the chain rule. A simple observation here is the following. We can indeed formulate many of these objectives as linear programs. After doing so, the constraints can be divided into groups of constraints, each corresponding to a small batch of data, and the optimization on each mini batch will satisfy their corresponding group of constraints. Let's look at the AUC as an example to check the LP form. Here, Zij is the variable to be optimized. Fxi is the score of sample xi predicted by a deep neural network. X plus and X minus here are the set of positive samples and negative samples. After solving this LP, we can get an estimate of the AUC based on this formulation. In fact, by strong duality, this estimate is provably a lower bound of AUC, which is not true for other softmax-based approximations. The formulation shown here in the previous slides extends readily to other objectives such as F-score, P at R, etc. We provide more details in our paper showing that LPs have a rich structure or expressivity and important in design custom loss functions, so please check it out. In a sense, by formulating these functions as LPs, we enable the use of mini batches and can compute the estimate of AUC once the LP is solved. Our basic workflow is shown here. Now, the remaining question is, how should we solve this LP within a deep neural network nicely? Over the last several years, at least a few papers have tackled this problem, but it is good to review the main challenges. Note that solving an LP in deep neural network is often not easy. The first challenge is that deep models require differentiability. Here's a demonstration of the linear program objective as a function of the variable to be optimized. We can see that in most areas, the function is flat. And what we want to use as a gradient in this flat area is tricky. Let's take a look at the one-dimensional case to get a clearer view. Here, fx is a function of x, and it's piecewise constant due to the nature of the LP. Now, look at the red point here. What should be the gradient here? If we use the gradient as 0, it won't lead us to the global optimum. It's obvious that in this case, we should go towards right-hand side at this point. And we can also do an approximation in order to get a function, in order to get a solution. However, in higher dimensions, constructing such approximations is involved and our solver should be able to solve it. But this is not all. Suppose this is a feasible set formed by the linear constraints, and this red point is the current guess of the decision variable. The green direction is the update direction where we want to go. Here, the update direction in this example is indeed correlated with the direction containing optimal solution, indicated in blue. However, note that after updating, the variable becomes invisible. So we need a projection operator that puts it back into the feasible set. This projection operator is needed at every iteration, which can be expensive and it's hard to define its gradient. As an example of the losses constructed using such constraints are Fincher-Young losses, which was studied in a nice paper last year. Moreover, the LPs derived from non-decomposable functions usually have the property that the number of constraints is usually much larger than the number of variables. Here, say A is of dimension m by n, m is usually much larger than n. In our neural network models, both the number of constraints and the number of variables are influenced by the mini-batch size, and the number of constraints are in addition influenced by the problem setting, like the number of classes. Ideally, we should be able to leverage this property within our solver for efficiency purposes. It turns out that Ovi had thought of many of these problems nearly 2 decades ago. Our solver is motivated by a beautiful paper from Ovi, which proposes solving linear programs exactly using a Newton method. Ovi's paper gives us a computationally viable alternative for solving LPs on GPUs. The key idea is to use piecewise quadratic function representation of the linear constraints in the LP to compute the optimal dual solution exactly, and then extract the primal solution by simply solving a linear system, which can be performed in finite time. At a high level, the Newton LP solver solves the problem as follows. First, we start from a given LP. We then solve an unconstrained version of the problem. The solution of this problem will provide us a set of active constraints in AZ less than or equal to B. Let's denote the set of active constraints as A tilde and B tilde. We can then get the optimal solution of the original LP simply by solving A tilde inverse times B tilde. But before apply the Newton method, we need to check whether Newton method will converge well for our purposes of solving LPs using mini batches, and whether the runtime will be acceptable. Our optimization procedure is to update the variable y utilizing the modified hashing. In our paper, we show that for our purposes, Newton's method has local quadratic convergence, which is good. Another important point is that usually Newton method requires a line search to find the step size, which is too expensive for deep nets. Our analysis shows that we can avoid the line search and use a constant step size for lambda under certain conditions. Our algorithm is shown here. First, we feed our LP, then we do k times updates using the Newton method. Then we compute the indices of active constraints and solve for the optimal solution X. To allow our solver to handle sparse inputs, our implementation was extended to support sparse operations for several commands in PyTorch. The first advantage of our solver is that it has quadratic local convergence, which means that we can use fewer iterations, and this leads to faster forward and backward paths and a smaller memory footprint. Recall that we can solve the optimal LP using only the active constraints. Thus, the problem size we solve become independent of m, which is the number of constraints, which makes the compute time even faster, especially for problems with large number of constraints, common for objectives we study here, but could equally well be applied to other general LPs where this happens. Further, we can use sufficient dimension reduction to further reduce the computational cost. Roughly, the idea is like this. We first have an original constraint matrix, and then we will apply a sampling matrix S. This will reduce the number of constraints. A more technical description is in the paper. This concludes a quick overview of what the technical part of the paper covers. Let's now see whether this idea works. Our first experiment is to optimize binary AUC score. The setting is like this. Assume we have some positive samples and some negative samples. We then construct imbalanced datasets by dropping negative samples according to a certain ratio. In this example, the positive ratio is 2/3. We conduct the experiments for 4 datasets and compare with directly optimizing cross-entropy and also the previous state-of-the-art approach called PPD. We can see that our method performs favorably relative to the baseline in most cases. Our approach also enables optimizing multi-class AUC. AUC OVA and AUC mu here are 2 different ways of computing multi-class AUC. We take the 90% drop rate on STL10 as an example and plot the AUC curves treating different classes as positive. We can see that this plot, we can see from this plot that our method performs better than optimizing cross-entropy loss in a manner that is stable. The next experiment optimizes the F1 score. We can see that our method also outperforms cross-entropy loss on these 4 datasets. Recently, a line of work proposes using black box solvers within a deep neural networks, which can often calculate the backward gradients by adding a perturbation noise. Although these works cannot solve non-decomposable objectives directly, they do have the potential to do so. Thus, we compare our solver with these ideas to see or to verify properties in terms of solving LPs. We first performed a runtime comparison for solving a batch of LPs of our solver and the solver in 30. We can see that our solver shown in orange runs much faster, and notably our backward cost is nearly 0 because the matrix needed for computing gradients has been computed during the forward pass and can be reused. We also compare with other 2 existing solvers on several important properties, including gradient support, GPU support, etc. Note that the black box solvers can also solve combinatorial problems, but here we only focus on utilizing them for our purposes, which is to solve LPs. Thanks for watching this video. The code is available, and the effort to integrate the solver with other libraries used in our community will be done soon. Please see our paper for more details and let us know what you think. Thank you.